Good morning, my students. We are going to make revision about the last part of physics. At first, what happens when the galvanometer, needle whose terminals are connected with this two solenoid will be deflected if one withdraws the magnet quickly from the coil because the number of turns of the coil is very large. Because the number of coil is very large, or the coil intercepted the lines of the magnetic flux, or the number of turns of the coil is suitable, or the number of turns is small. Again, the pointer of the galvanometer needle whose terminals are connected with the solenoid. This is the solenoid. Its terminals connected with the moving coil galvanometer has zero centered. This is called zero. The pointer of moving coil galvanometer. The galvanometer needle whose terminals are connected to solenoids will be deflected if one withdraws the magnet quickly. If the magnet is draws quickly from the solenoid, because the number of the coil turns is very large, the coil intercepted of the line flux, the number of turns is suitable, the number of turns is small. The deflection of the moving coil galvanometers produces or indicates the presence of induced current. Induced current due to the change in magnetic flux. Lines. When we move toward the solenoid, the magnetic flux increases. When we move away from it, the magnetic flux decreases. This means that the deflection depends on the coil intercepts the line of the magnetic flux. This is the answer. This is the right answer. If the number of turns of the coil is 20 turns, this is the number of turns of the coil. When the magnet brought close to it, the magnetic flux increases. Magnetic flux, not magnetic flux density. Because magnetic flux measured by Weber, magnetic flux density measured by Tesla. This is magnetic flux phi m during time delta t with the value produced EMF according to Faraday's law. EMF induced equal minus n delta phi m over delta t. In this state, number of turns is 20. At 20 equal EMF equal 20 times delta phi m 0.2 divided time 0.02. This is the method which can be used to determine the value of induced EMF. This sign indicates lens rule. Lens rule is added to indicate lens rule. When we approach the magnet to the coil, we observe a small force which repel it. When it is pulled out, we observe force of attraction to attract the magnet. 2 cancel with 2, 0.01, 100 divided 10, 0 cancel with 0, 10, 20 equal to 100. The answer is 200 volt. The answer is 200 volt. In another question, the needle of the galvanometer whose terminals are connected with the solenoid deflects on the withdrawal of the magnet in a direction opposite to that which occurs in plunging the magnet into the coil, because an induced current is generated in a direction opposite that on plunging the magnet. Electric current is generated, number of magnetic flux lines decreases, number of the magnetic flux changes, number of magnetic flux it changes. Why? This question indicates the needle of the galvanometer whose terminal are connected with the solenoid coil deflects. This deflection in a direction that oppose the change producing it according to Lenz's rule. This means that induced current is generated in the opposite direction that plunging the magnetic field. This is the answer of this question. And the opposite figure, in this figure, this is a magnet, this is a lamp, this is a battery and switch. When moving the magnet in the shown direction, the light intensity of the lamp, what happens to the light intensity of the lamp? From this figure, we observe that the battery produces electric current intensity. This is the direction of the current intensity by the battery. This means that the lamp glow up, flashes. This magnet is pulled out. This means that attractive force is produced. This pole is south, this is south, this is north. The direction of the induced current, according to Ampere right-hand rule, if the thumb points to the direction of the north pole, the other finger points to the direction of the current. This means that the direction of the induced current in this direction. The current intensity increases, the lamp flashes increases, the lamp increases. The light intensity of the lamp increases. And the opposite figure is spiral spring connected with the magnet, and this is moving coil galvanometer, and this is the solenoid. A magnet is suspended in a spring free to move in and out of the coil connected to the galvanometer, having 0 in the middle. It's a scale. When the magnet moves up and down, the galvanometer reading swing from left to right and vice versa, stops at left, stops at right, stops at 0. If the magnet vibrates, longing and pulled out from the solenoid, there is a change in magnetic flux, but in opposite direction. This means that the magnetic needle vibrates to left and to right, from left to right. This is the guide answer for it. This is the guide answer for it. Okay? Which of the following relation represents Faraday's law for electromagnetic induction? Faraday's law, EMF, NBA tan, no tan, no tan. NBA sine theta minus PA sine theta. It is more correct. This is correct, but this is more correct because it contains negative sign according to Lenz's rule. According to Lenz's rule. Another question. Induced EMF generated when a magnet moves into or pulled away out of the coil according to different to the direction. The intensity of electric current, the length of the wire, the number of magnetic flux, the magnetic strength and the velocity with the time moves, and the number of turns. Number C, cross-sectional area, mass per unit length of the coil, the type of the wire, of the D, density, flux density, time, electric current. The answer is B. The answer is B. The next question. The following cases represent the change in magnetic flux in a circular coil of N turns. Which of them causes the maximum EMF? EMF maximum. Again, the following cases represent the change in magnetic flux in a circular coil of number of turns N. Which of them causes maximum EMF? Changing the flux from 2 Weber to 2.1 Weber within 10 power negative 4 seconds. Changing flux 0.2 Weber to 4 Weber with 0.2 seconds. Changing flux of 1 Weber to 20 Weber within 10 seconds. Changing flux from 0.01 Weber to 0.02 Weber within 0.2 seconds. Any choice can be applied upon the rule epsilon induced equal minus n delta phi m divided delta t. In each coil, the number is n, is constant, does not change. The changing due to phi m over delta t. To obtain maximum induced EMF, we need to obtain maximum EMF. We need high magnetic flux density and the small time. So we can use to calculate it 2.1 minus 2 equals 0.1. Divided 10 power negative 4. 10 power negative 4 up 10 power 4 equals 0.1 times 10 power 4 equal 10,000. The second, 0.2 and 4. The difference between them, 3.8 divided 0.2. The third, 20 minus 1 divided 10. The fourth, 0.01 to 0.02. The difference between them equals 0.01 divided 0.2. This means that the first is the right answer for it. Number 10. Which of the following will cause an induced current of the coil wire? Cause an induced current in a coil. A magnet resting near the coil, the constant field of the earth passing through the coil, a magnet being moved into or out of the coil, the wire carrying constant current near the coil. Induce the current in the coil of wire due to moving magnet, changing the magnetic field, which produced kinetic, it produced change in magnetic flux, which is directly proportional with the induced EMF, which is directly proportional with the induced EMF. Doubling the diameter of the loop wire produces which kind of the change on the EMF, assuming all the other factors remain constant? Induced EMF increased 4 times. Induced EMF increased to its double value. Increased EMF decreases to half value. Induced EMF is unchanged. Again, doubling the diameter. Doubling the diameter. Area equal by R square. When the diameter is doubled, cross-sectional area increases 4 times. When we double area. Area square, radius square تبقى equal 4. The area becomes 4 times. Epsilon induced equal minus N delta BA over delta T. When the area increase 4 times, induced EMF increase 4 times. In this side, when the north move down, the P is north and A is south. By applying Ampere right-hand rule, we can determine the direction of the current. The direction of the current. The thumb will point to the direction of the north. The other finger will point to the direction of the magnetic field. So the current transfer from 1 to 2, and the magnet pole formed at pole A is south pole. A is south pole, and the current transfer from A to B. Goodbye and good luck, my students.